Hi, everyone, and welcome to this episode of the University Scholars Series. It's exciting today. We have Professor Virginia Sanfratella from Design, whose presentation, Play, Clay, and Chardonnay, I am very confident is going to be really outstanding and interesting. We have a few housekeeping issues that we have to take care of first. The first is thank yous. Of course, my colleagues in the office of the provost have been doing a ton of work to make sure this gets off the ground, as is the colleagues in the King Library. We have the College of Humanities, the Spartan Bookstore, and the Division of Research and Innovation as well, who've all helped make this possible. A couple of quick announcements. If you need captioning, it is available. You see the live transcript button on the bottom of your screen. You could push that at any time. And we will be recording this webinar today so that we have an archive of it as well. So please make sure that you understand that everything is being captured. If you have a question today, we're going to use the Q&A function, and you can just simply click on the Q&A and type your question in. I'll be moderating and working with Virginia to make sure we get questions answered in a timely manner. Before going any further, it's important that we recognize our local community and our local tribe through the land acknowledgement. The San Jose State University community recognizes that the present day Muwekwe Ohlone tribe, with an enrolled Bureau of Indian Affairs documented membership of over 550, is comprised of all of the known surviving American Indian lineages aboriginal to the San Francisco Bay region, who trace their ancestry through the mission Santa Clara, San Jose, and Dolores during the advent of the Hispano-European Empire into Alta California, and who are the successors and living members of the sovereign, historic, previously federally recognized Verona Band of Alameda County. Furthermore, the San Jose State University community recognizes that the university established within the Tamimine Ohlone speaking tribal ethno-historic territory, which, based on the unratified federal treaties of 1851 to 1852, includes the unceded ancestral lands of the Muwekwe Ohlone tribe of the San Francisco Bay Area. Some of the enrolled Muwekwe lineages are descended from direct ancestors from the Tamiyan Ohlone tribal territories, whose ancestors had affiliation with Mission Santa Clara. The San Jose State University community also recognizes the importance of this land to the indigenous Muwekwe Ohlone people of this region, and consistent with our principles of community and diversity, strives to be good stewards on behalf of the Muwekwe Ohlone tribe whose land we occupy. With that, let me please just take a moment to introduce today's speaker, Virginia Sanfratella, who again is a professor and currently chair of the Department of Design here at San Jose State University. She has had an amazing career, and we are very fortunate to have her here, as she's been here since 2010. Having completed degrees at North Carolina State, at Columbia, before making her way through a number of different positions in some very outstanding institutions, including Clemson, Queensland, and Brisbane, Berkeley, and MIT. As I said, she's been here since 2010. She does a lot of work in the area of design. She has her own firms that work in architecture, and she's not just an author, but an activist and a thought leader in a number of different areas, including additive manufacturing, architecture, and interior design. In 2014, one of her creative practices, Raul Sanfratella with Ronald Raul, was named an emerging voice by the Architectural League of New York, which is one of the most coveted awards in North American architecture. In 2016, they also won the Digital Practice Award, and in 2020 were awarded the Art and Technology Award from the Los Angeles County Museum of Art. Most recently, the Pink Seesaws Project has won the Beasley Design of the Year Award as well. Not only is she an outstanding designer, she's also an author, and her most recent book is co-authored called Printing Architecture: Innovative Recipes for 3D Printing. I could go on and do a lot more of introduction, but I think everyone in the audience really would like to hear from Professor Sam Fratello. So I'm going to turn it over to her now and thank her for being here today.
Thank you so much, Ben, for that introduction. I'm really excited to have the opportunity to lecture at my own university and to share the research and the creative activities that I've been doing for the last 11 years now at SJSU with friends and colleagues and students. So thank you, Ben, very much for inviting me to be here today. Let me share my screen and we can get started. Okay, can you see that? All right, so the title of my lecture today is Play, Clay, and Chardonnay. And I'd like to start by talking about Chardonnay. So one of the things that I've been instrumental in developing over the last 11 years at SJSU is a methodology for thinking about how we can use local materials or materials that are in the waste stream in additive manufacturing. And of course, we all know that Chardonnay is a material that is local to Santa Clara County, as well as to Napa and Sonoma as well in terms of wine production. What you might not know is that the skins and the seeds of the grapes are actually an agricultural waste material. These don't go into the wine itself, and they're left in the field to rot. And sometimes they're used as fodder for I guess feed for animals. And so I've been able to take this material, the skins and the seeds, and work with a manufacturer who's drying it in order to create a powder that can be used for baking, but it's also a suitable material for 3D printing. And here you can see these Chardonnay wine goblets that have been 3D printed out of the Chardonnay grape skins and seeds themselves. This is a 3D printed building block made out of the Chardonnay grape skins. The texture on the surface is that of a grape skin. And this building block is then radially rayed to create this wine bucket, which was made for the champagne manufacturer Pierre Jouet. Salt is another material that's local to the San Francisco Bay Area. This is a material that has been harvested from the Bay for over 150 years. At the height of its production, 150 million tons of salt was harvested. Now it's more like 150,000 tons each year, because about 30 acres of the crystallizer fields have been given back to the Bay Area and for wetlands reclamation. But this material has been used to make materials and objects like these 3D printed salt shakers, which you can see here. And these are functional. The salt is bound on the exterior and then it's loose on the interior, so the salt can be shaken out. Sawdust, this is another material that's in the waste stream. Of course, a lot of the wood material in the Bay Area that we use comes from the Sierra Nevadas. And about 7 million tons of wood waste are generated every year by the construction industry. And a percentage of that can be used for additive manufacturing. And we've worked to think about how we might take the sawdust and combine it with other inherently sticky materials that can be used in the fabrication of 3D printed sawdust components, which you can see here in this vessel or dish, for example. So normally when we work with wood, it's subtractively, we use it by cutting, milling, sawing. And in this case, we're taking those particles and adding them together to create a very complex and intricate structure. Coffee, this is another material that is in the waste stream. Of course, here in the Bay Area, I drink a cup of coffee every morning and I have coffee grounds, which traditionally were thrown away. But this is also a kind of universal material that can be considered for recycling and additive manufacturing, because coffee has made its way all around the world. So you can use coffee grounds, as I mentioned, in 3D printing, and which I've used here to create this 3D printed coffee pot. And I've also worked with manufacturers to use the coffee cherry for 3D printing. So the cherry, much like the Chardonnay, is a part of the fruit that surrounds the bean. And the bean, of course, goes along to be roasted, but the fruit is left in the field to rot, and it is an agricultural waste material. And that fruit can, again, like the Chardonnay, be dehydrated and pulverized and turned into a flour that can be used for powder-based 3D printing. And that coffee cherry is used to 3D print these coffee cups, which you can see here. Sugar is another material that's quite easy to 3D print with because of its inherent stickiness. And what you see here are 3D printed sugar spoons in volumes corresponding to 1 teaspoon, 2 teaspoons, 1 tablespoon, and beyond. And you can stir your 3D printed sugar spoon down into your coffee cup to flavor your coffee with sweetener. Tea, like coffee, is another global material that has waste in the field, but also tea fluff can be found on the factory floor, or tea leaves, of course, are another waste product that we all find in our homes and restaurants throughout the world. So the tea can be used for additive manufacturing, which is shown here quite literally in these 3D printed teaspoons. Again, in volumes corresponding to 1, 2 teaspoons. And there are, of course, teacups and teapots. Curry is another material that I was interested in developing for additive manufacturing, mostly because a lot of the agricultural materials that I had printed with were a shade of brown. And I was interested in seeing if I could experiment with other colors. And of course, the curry is quite bright because of the turmeric in it. But one thing that I realized as I was printing with the curry, and you can see here in this furry curry casserole dish, the sort of bright, vivid orangeness of it. But one thing that I realized while making it was that the fragrance or the aroma of the curry just pervaded all of the spaces that I was working in. So the entire lab smelled like curry. And I've taken this to interiors, and it is an object that literally seasons the room in which it's placed. And the intent here is not only to use this object to kind of season or flavor a space, but it's also intended to give flavor to what's inside the dish itself. So if you look closely, you can see that the interior of this dish is left unfinished, so that if you put rice or noodles in it, they would start to take on the flavor of the 3D printed dish or object itself. And those objects are housed in a small 3D printed building here in Oakland, California, which is called the Cabin of 3D Printed Curiosities. And this is one of the moments where we have been able to take our experiments with additive manufacturing and novel materials and scale it up and move out of the realm of objects and into the realm of interior design and architecture. So here you see some of the objects that I've talked about on the table and the shelves and the back wall. The interior of the cabin itself is 3D printed out of bioplastic. And this material in the United States is usually made out of corn, but it can be made out of other starchy agricultural materials as well. The walls have a kind of beautiful soft luster or sheen, which is a product of this material. And you can see a floral motif that's embossed into the surface of these tiles that are on the wall. And this is in reference to traditional pressed tin tile ceilings or walls that you might find in this traditional Victorian neighborhood where the cabin is located. One of the main differences, aside from the material, of course, is that the tiles in this case are all unique, because 3D printing doesn't care if you're printing 1,000 of the same thing or 1,000 different things. So variation, complexity are free. On a traditional pressed tin wall or ceiling, every tile would be the same because it would have been created from one master. The furniture here, the chair, is also 3D printed out of bioplastic, and the coffee table itself is made using nylon. One thing we discovered during the process of making this building is that the bioplastic is always translucent. It doesn't matter if you're buying the opaque version of the bioplastic or the translucent. When backlit, you can always see through it. So we decided to backlight these bioplastic panels with LED lights to illuminate the interior. And the lights change color to change the mood and can be used for different programming throughout different times of day, which you can see here. And as you back out of the cabin and we start to look at the front facade, the surface is made out of some of the different materials that we've been experimenting with over the years. So there are planter tiles that hold succulents, which thrive in the Northern California landscape. And the tiles are made out of different materials. So for example, the dark brown tiles that you see on the surface are made out of Chardonnay, and the light brown tiles are made out of sawdust from the Sierra Nevadas. And the sort of off-white tiles are made out of cement. And sometimes we just recycle those materials together. We might mix cement and Chardonnay and create a new color tile. And we recycle our own materials into new prints. And we had the good fortune to, I think, build this cabin around 2018, at the time that San Francisco and Berkeley and Oakland were all rethinking their building codes for accessory dwelling units. And they increased the square footage that one could build with. And they also decided to eliminate building department design review. So because we didn't have to go through the building department, we didn't have to submit these materials for approval by the city. So we thought this was a really good opportunity to test these materials that we had been experimenting with in the lab in the actual outdoors and think about how they would survive over time in our climate, which is foggy and humid and wet, but also temperate. So here you can see the tiles the first day that we installed them. And then over the years, you can see how they've weathered and changed and how entropy has affected the coloration. But they're actually quite beautiful in their aged state. And they've reached this sort of maturity, I think, that gives them this sort of warm, really warm coloration. The east and west walls of the building and the roof are made out of 3D printed clay from California. These clay tiles are called the seed stitch tiles. And we call them seed stitch because this is a traditional technique that's used in knitting, because it looks as if seeds have been strewn across the surface of the tiles, and they have this bumpy quality. In this case, we printed about 5,000 tiles to cover the building, but there's only one design. And we use the sort of gravity or ambient humidity or weight of the material itself to allow for variation to occur, like in the way the tiles sort of flip up on the corner here. And these tiles make this very beautiful zigzag pattern across the surface of the building. And there's a really lovely play of light and shadow, and the vines and the plants from the garden are starting to weave their way into the structure to create a bridge between the landscape and the architecture itself. So clay, this is another material that we've been experimenting with from the very beginning. About 11 years ago in 2010, one of the first materials we printed with was powdered ball clay and powdered porcelain, and we used it much in the same way that you've seen in the last projects that I've presented. But more recently, we've started to paste extrude clay, which you can see here. And we've also developed a way of not having to 3D model forms in the computer, but literally working the G code, which is the language that the 3D printer speaks, to take that line of clay for a walk. And what we discovered is that we have the ability to make these very loopy looking surfaces that are textured. And sometimes failures happen, right? Like the clay breaks, which you can see here because the loop is too long. But we've decided to embrace those errors and to incorporate them into our designs, which you can see here. And one of the beautiful things about working with the G code itself is that we're able very easily and very quickly to have a tremendous amount of variation. So if you look at, I think there are about 90 or 100 of these vessels that we made, there are actually only about 3 or 4 different forms, but what makes them different and unique and distinct is that the texture of the loops and the patterns on the surface of these vessels is different every time. So we're able to have variation within repetition. And one of the things that we've always wanted to do is to scale this up. So we've used this material and this technology to make small objects such as tabletop accessories and vases and utensils. But one of the big questions has been, how do we take this to the scale of architecture? And you can see here in this image on the left, an example of a building in Africa, a historic building that is made out of mud that has this beautiful decorative surface, which in some ways is reminiscent of some of the textures that we're creating through 3D printing as well. And this decorative surface is not only beautiful, but it's also quite functional. If you look closely, you can see that it's the scaffolding that the local villagers use to climb up the building to replaster it every year after the monsoons. And so finally, this year in 2020, this past summer, we were able to create a large 3D printed structure out of mud using the software and using this technology. And we call this project Mud Frontiers. Mud stands for mud, of course, because we're printing with mud, but also mobility, ubiquity, and democracy. Because we're working at, I think, the frontiers between the United States and Mexico, the historic frontier here. This is happening in the San Luis Valley, which is a large high alpine valley that spans southern Colorado and northern New Mexico. We're also working at technological frontiers. And we are thinking about how we can continue indigenous building practices and combine it with additive manufacturing and digital fabrication technologies. So close to us in the San Luis Valley is the Taos Pueblo, which you can see here in this photograph. This building is made out of adobe or mud bricks, and it's mud plastered. And this building has been here for thousands of years. It is the oldest continuously occupied building in the United States. And so it's on these traditions that we would like to build. This is our mobile robotic setup. So this is a robotic arm slash 3D printer that's very lightweight. It can be carried by 1 or 2 people from one site to another. And in this particular setup, it has a RAM attached to it, which is this plexiglass tube that can be filled with clay. But for our 3D printing applications out in the field, we've taken off that RAM and we've connected the robotic arm to a continuous flow hopper, which you can see in our fabrication setup here on the right. So at the center of this 3D printed mud structure is the robot. It is holding a rubber tube, which is connected back to the continuous flow hopper. And then we are mixing mud and putting it into that hopper and continuously pumping it through the tube while the robot moves it around. And this allows us to make structures that are larger than the robot itself. We're using literally the ground beneath your feet. We're using a ubiquitous material. Of course, soil, mud, earth can be found in every country around the world. And we're mixing that soil with chopped straw for increased tensile strength and to wick out some of the moisture as the adobe or the mud is drying. And of course, we're mixing it with water. And democracy. So as part of this project, Mud Frontiers, we've created a software called Potterware that runs in the cloud. So you don't have to know how to 3D model anything to 3D print. You can simply use these sliders that you see on the right-hand side of the screen, move them back and forth to create a profile for your vessel or to create waves or loops on the surface of your vessel. And we've been experimenting with non-planar options and giving users the ability to make multiple prints as well in this easy to use software that runs in the cloud. And these are some of the early experiments that we did here in the San Luis Valley. And we kind of conceptualized these under 4 different themes. This one we call the beacon, and it's quite literally a study in lightness. So we use the robot arm to take one single line of clay along a path that has both convex and concave openings to see how lightweight of a structure we could print. And because we were interested in light, we decided to illuminate the structure to show off the layers of mud and the concave and the convex surfaces on this structure itself. This is the lookout, and this was an exploration into structure. We wanted to know if we could print something that would be strong enough to support the weight of the human body. So there are stairs here, and which are underpinned by just 3D printed mud. And of course, this lookout or this platform on top is solid underneath as well. And this is what it looks like underneath the stairs. We don't have the ability to retract with this particular printer. So there's a continuous flow of mud, and we are creating this Pizzelli-like pattern or structure underneath the stairs and the landing to give support for the body. And we also imagined that these air spaces which would exist in the gaps in between the sine waves could also have insulative properties for future architectural applications as well. This is the kiln. This might be the world's first 3D printed kiln, but it's printed out of mud. It's a double wall structure. And so we are taking advantage of the air that is in between the double wall, kind of inside these fingers. And we've dug a hole for pit firing, ceramics, and this opening here faces south, so the wind blows in, it kind of creates a vortex on the interior of the building where we can fire some of the smaller objects that we're making as well. So this tagine and bowl and other serving vessels are made out of micaceous clay that we're digging kind of wildly from the mountains just south of us. And the 4th structure is called the hearth. And in this particular instance, we were interested in thinking about how structure could be decorative. So when we're printing this mud, it's of course quite wet, and we can print about between 14 and 18 inches at a time before we have to stop and let it dry. So this particular structure has an inner and an outer layer of mud, and we use these sticks, these juniper sticks, to tie those 2 layers together. And because we were inserting the wood into the structure, we were able to print a little bit higher. And of course, one of the things that I really love about this is of course the increased strength, but also the fuzziness or furriness. And on the interior, there's a hearth and a 3D printed bench where friends can gather together and be protected within this enclosure. And our research in developing these 4 smaller projects has led us to create a larger occupiable structure, which we call the Casa Covida. which is a house for cohabitation during the time of COVID. And it is something that we have made over the course of this past year. The Casa Covida brings together these indigenous building technologies and combines it with digital fabrication. And I think one of the things that we have been able to do this year is to create this fourth axis, or this wooden rail, that allows us to take the robot for a walk so that we can print more than one circle at a time. So here you see the robot is the tall vertical element at the end of the 3D print. So we print about 18 inches. We move the robot down, we print another circle about 18 inches high, move the robot down, print a third time. And by the time we finish this third room, the first one is dry and we can take the robot back. So in the same amount of time that we would print one object before, we can now print 3. So we've created a house that's made out of these 3 contiguous spaces, and are thinking about them as a place to enter and gather, a room for dreaming or sleeping, and a room for bathing. And here you can see the robot extruding the mud, putting down the walls for the Casa Covida. And this particular building has an inner layer and an outer layer. They're both sine waves, and the frequency of the inner layer is double that of the outer layer, so that they touch or kiss and they can support each other as we build up. And at the top, the walls come in to create frustum or dome-like shape. Another innovation in this particular building is that we put the robot on top of a plywood box so that we could go taller. The robot is only about 7 feet tall, and this building is 12 feet tall. And here you can see my partner on his cell phone. He's not texting, he's actually driving the robot. So the robot is Wi-Fi enabled, and he can use the smartphone just to control the speed of the arm as it's moving and the extrusion rate as it's pushing the clay out from the nozzle onto the surface of the building. In this particular project, we also introduced lintels into the structure so that we could have openings like windows and doors. So we used the local beetle kill pine, which you can see here, this black line over the door, and we just print on top of it. So we're able to now have more conventional openings so that you can move in and out through the building. And here we are printing the last layer of the oculus at the top of the building. And here's the final Casa Covida. You can see the illumination from the hearth on the inside, and these 3 volumes that are nestled together, which are intended to be a retreat or a place for quarantining with one other person as a space of cohabitation and togetherness. When you enter the Casa Covida, the first thing that you touch is the door handle, which we've made as well. We've used bioplastic to 3D print a master, which we then cast in a mud mold. And we are burning out the bioplastic 3D print and then replacing that with aluminum to create this metal door handle. We, like many other people, acquired a pet during COVID. We have a cat, and it turns out that Friskies cat food cans are 100% aluminum. They are perfect for this lost wax or lost PLA method of casting. In the first room, there's a hearth where 2 people can gather around the fire and cook and prepare a meal together. We've also 3D printed all of the cookware, the tagines and the bean pots and the serving dishes using the local wild micaceous clay that we've harvested from the mountains and the fields around us. And here's a close-up view of one of the bean pots, the form of which is based on, again, the traditional bean pot forms, which you might find in the Taos or the Picoris pueblos. And the clay has mica in it, which does a really good job of observing thermal shock. So you can put this 3D printed fired piece directly on the fire and it will retain its integrity and strength. You can cook in it. Here's a view into the room for sleeping. A window with a view of the sunset beyond. And we made an elevated platform that's covered with churro sheep skins from the local sheep. And we worked with an indigenous weaver to create these textiles for the Casa Covida, which is a really fascinating story. This is a young fashion designer who's in New York, who was intending to graduate last spring, but of course he had to go home. And he, like many of our students, didn't have access to the tools that he normally has access to in his labs, like his sewing machines or his sergers. So he was at home and he was wondering, well, what will I do? And his aunt gave him her loom and taught him about his own family history and explained to him that he comes from a family of weavers. And so we worked with him to develop these custom textiles that have the motifs which come from the building itself. So if you look closely, you can see on the pillow here the floor plan of the Casa Covida. So in the center is the circle with the door and the fireplace, and to the left is the bed, and to the right is the room for bathing. And here on the blanket is the reflected ceiling plan of the oculus in the room for bathing, and the bathtub itself. So the blue circle represents the water, the white circle, the rim of the bathtub, and the black line, the drain that allows you to drain the water back out into the field, which you can see here in this view from above of the room for bathing. So the blueness of the water, which is surrounded by polished river rocks. And when you're in the water, of course, you can look up at the sky through the oculus. And finally, play. So as a way of talking about play, I'd like to share with you a set of instructions for how to build a teeter-totter. The first thing you need to do when you're going to build a teeter-totter is choose a site. So the site that we chose is the border between the United States and Mexico. And just to give you a sense of scale, the border, the political border, is almost 2,000 miles long. And since 2006, when George W. Bush established the Secure Fence Act, around 800 miles of border wall have been constructed. And there are different types of wall. There are what's known as a bollard wall. And this is a wall that has about usually 18 to 20 foot high vertical steel posts that are filled with concrete. And these are used to prevent pedestrians, of course, from moving from one side to the other, but also to prevent vehicles from passing from one side to another. There is pedestrian fencing. And this, of course, is just to prevent people from moving across the border. And these walls are typically made out of welded wire mesh or perforated metal, and this allows the Border Patrol to see what's happening on both sides of the border. There's anti-ram wall. This is intended to prevent vehicles that are loaded up with like 40 tons to ram into the wall or to pass through the wall. Supposedly, it's impossible to cut through this wall. And these walls go at least 6 feet below the ground to prevent tunneling as well. And then there are landing mat walls. And these are some of the oldest types of walls that are made out of repurposed Vietnam era landing mats. And these have all been almost all replaced. They're all proposed to be replaced under the more recent Trump administration acts. And then of course, there's the beautiful floating fence that sits atop the sand dunes. Since 2006, the United States has spent $3.4 billion constructing this wall. And it's estimated that another $49 billion will be needed to construct and maintain the border wall over the next 25 years. So just to give you a sense of perspective, what can you get for this amount of money? Well, we could build 300 SAP centers, or 500 miles of the High Line, or 350 Broad museums. So this is money that could be spent on cultural endeavors and not on a wall, which in my opinion doesn't work very well anyway, which you can see here. So the research for the border wall is conducted at Texas A&M University at the Sandia Laboratories. And the way they conduct this research is by building wall prototypes and loading trucks with 40 tons of weight and ramming them into the walls. So you can imagine the expense associated with building the walls, not to mention acquiring the vehicles that are then destroyed by ramming them into the walls themselves. And there's another kind of research happening on the other side of the border. And this is very inexpensive, very lightweight research, which is mostly comprised of these mobile units that allow trucks to drive up and over the wall, which sometimes works very well, which you can see here. And sometimes doesn't. This is an example of a truck that got stuck on top of the floating fence, and its occupants were forced to flee before the Border Patrol arrived. And then there are the horrors of the wall. Since 1994, nearly 10,000 people have died trying to cross the border. And of course, hundreds of children have been separated from their parents at the border. Over 30 laws were waived for the construction of the wall. This is the highest law of the land. So Native American preservation acts have been overridden, wildlife and environmental acts have been overridden, and this ensures that the wall can and will be built. In order to construct the wall, it has to be built on the United States side of the political boundary. And because of the avulsions in the Rio Grande, sometimes this means that the wall is built 2 miles into the United States, ceding over a lot of property to the Mexican side of the border. And this property includes houses, it includes parks, golf courses, or in the case of Brownsville, Texas, half of the University of Texas is intended to be ceded over to the Mexican side of the border. Now, I also want to point out there are lots of fun and exciting things that happen at the border as well. So here, for example, you can see a binational yoga class. And what I love about this photo is that everyone is in monument pose. And you can see here in the background, the monument, which is one of the original markers of the border between the United States and Mexico. Here in this photograph, you can see a Border Patrol agent buying an ice cream from a vendor on the Mexican side of the border. And this seems totally normal, right? He slips some money through the fence, the vendor slips some ice cream through the fence. And it seems like this is something that should be totally normal and fun, right? But in fact, this is completely illegal and constitutes illegal trade across the border between the United States and Mexico. Volleyball is often played across the border between the United States and Mexico. Interestingly, the game of volleyball was invented by a classmate of the inventor of basketball. His name was James Naismith, and he thought that basketball was too hard, and he wanted to create a more equitable game that everyone could play and enjoy together. So volleyball has been played at the border between the United States and Mexico for many, many years. This is the Festival Binacional, which takes place every year in between Naco, Sonora, and Naco, Arizona. This is a photograph from the 1970s, maybe one of these first binational volleyball games. It's still played today, which you can see in this photograph. And I'd like to point out what is one of the most interesting things about this photograph for me is that Tecate somehow is allowed to span the border between the United States and Mexico, which I think points out that the border wall is not only a political construct, but it is becoming a cultural one as well, which I'd like to show you here in this advertisement for beer.
The time has come for a wall. A tremendous wall. The best wall. The Tecate Beer Wall. A wall that brings us together. This wall might be small, but it's going to be huge. You're welcome, America.
So it's these things, these events and acts that are absurd, that are horrific, and sometimes really funny, that have prompted us to intervene in this landscape by smuggling in design. And we have imagined proposals for the border wall that we present in the form of souvenirs or recuerdos that include postcards and snow globes and keychains in order to speak to the resilience of the landscape and the people who live here at the border. And by doing it in these small souvenirs or in the form of these small souvenirs, we make the border small, we make it diminutive. And we hope that by presenting the work this way, it disempowers the wall itself. And what better way to do that than to design a teeter-totter, an active play that speaks to how actions that take place on one side have effects and consequences on the other. So when choosing a site for our teeter-totter, we chose this bollard wall between Anapra, Mexico, and Sunland Park, New Mexico. And we chose this site because the village of Anapra comes up very close to the wall, in some cases about 3 feet away from the wall. It's a community that has a lot of families and children. It's a place that you can walk up to the wall, and children are actually known sometimes to kind of climb or play on the wall here. So we knew that this would be a good spot for the teeter-totters. Next, decide how thrilling or dangerous the ride should be. So when we were first designing the teeter-totter wall, we knew we wanted to install it on the 18-foot high bollard wall in Anapra. And we designed these really long teeter-totters that would have a fulcrum, which would be halfway up the wall, which is about 9 feet tall, which would lift the riders maybe 18 feet up into the air. Incredibly thrilling, but also maybe incredibly dangerous. This might be why we were never able to get permission to build the teeter-totters. And we did ask a few times. We were never told no, but we were also never told yes. So in subsequent proposals, we decided to make a smaller, more viable version of the teeter-totter. So in this sketch, the teeter-totter is 14 feet long, and the fulcrum is 2 feet off the ground, which lifts the rider 4 feet up into the air, just high enough so that your feet don't touch the ground, which still allows the ride to be a little bit thrilling and exciting. We designed the horizontal components to slide exactly in between the vertical spaces of the bollard wall, with seats and handlebars that could be attached after the horizontal component had been slipped through the wall by the user on the other side. And the details matter. So we worked with Colectivo Chopeki and Taller Herreria in Juarez to fabricate the teeter-totters, to work out the details of how they would fit together. And they helped us smuggle in the design to make sure it would really work. So here you can see a photograph of the fulcrum, which has a notch in it, and it slides on top of the steel angle at the bottom of the wall. And there's a key, which is tightened from the Mexican side of the border. Banana bicycle seats add cushioning, a little bit of levity, and color. They have sparkles and metallic stripes on them. There are rubber grips, which make it easy to hold on to the handles. And there's a horn, which allows you to catch the attention of the rider on the other side of the border. The color pink is a color that is familiar to everyone in Juarez. Here you can see the crosses, which are placed in the locations where the bodies of women were killed during the femicides in the 1990s. So throughout the city, you can find these crosses. They're painted this color pink, and everyone knows what this color means and what it represents. So we decided to paint the teeter-totters pink as a form of resistance. And finally, you have to test it out. So on July 27th, we took our teeter-totters to the border from the Mexican side, and we stabbed the dragon. We passed them through the fence with the intent of riding the border between the United States and Mexico. And we knew we had to do it quickly because we might only have 5 or 6 minutes before the Border Patrol showed up to shut us down. And for 40 minutes, we were able to show that play can be an act of resistance. And we were able to make meaningful connections between adults and children along the border as we rode the teeter-totters. The border at this time for us became a fulcrum for US and Mexico relations. And most of the people who showed up that day were women and children, and they stood strong. You know, they weren't afraid of the Border Patrol, and they weren't afraid of the Mexican police, and they told them to go away, that we are here to play and to be together. And they created this kind of safe, protected space just by virtue of the fact of who they were. And we learned that women and children with really inexpensive pink sticks could break down a barrier, a $1 billion barrier that was created by a government. And it made us think that as architects and designers, we shouldn't be creating walls, but thinking about the spaces and the people in between them instead. So in conclusion, I want to leave you with the words of Archimedes. Give me a lever long enough and a fulcrum on which to place it, and I shall move the world. Thank you.
All right. Well, thank you. That was amazing. And lots of great questions. Unfortunately, we don't have a ton of time for them. So I want to kind of bulk a couple together and maybe get your reactions to this. For colleagues who are interested, we did record this and it will be on the ScholarWorks page. We'll make sure we distribute it to everybody so that, you know, everyone has access and they look through it. And I'm sure, Virginia, you're going to get more questions via email and other sorts of things. The two big kinds of questions that come out, one is like a conceptual one around the houses and other things, which tie to the ways in which these look like archaeological and prehistoric sorts of sites. Were you taking any cues from that history of architecture, and why the open roofs and so forth? Was that a design principle or just a challenge for building the roof? Talk through some of those architectural sorts of connections to perhaps the prehistoric world or some of the other things you were thinking about.
Yeah, I think that must be with the Mud Frontiers project, right?
Yes, yeah.
So yeah, I mean, we often like to look back, to look forward, to look at history, right? And think about what technologies have been around for, you know, thousands of years. And in some cases, we've lost these technologies, and not always for good reasons, right? Like, you know, for thousands of years, earth was the most pervasive building material, and cement took over about 100 years ago. But we all know that cement is one of the most polluting materials on our planet. And so I think we actually have to think about how we go back to building with mud and clay because of the thermal mass properties or the flywheel effect that this material has, right? In places like this is the southwestern part of the United States, right, where you have a big temperature differential. And we've forgotten how to build with those materials, but they're much better for our environment, right? So I think we're looking at them and thinking about how they can be transformed for, you know, 21st century applications, because we have different program needs than we had 1,000 years ago. We have different technologies than we had 1,000 years ago. So we're trying to merge these together. The reason there's no roof is that, well, it's the robot is printing out, right? And then for us to come in is very hard. So so there's a chance that the roof would collapse, right? So we're not there yet, but we're going to get there. Maybe 2022, you're going to see a building with a roof. I promise. It's on my list of things to do.
As long as it's on the list, I think we'll all give you, some flex. So another set of questions come up to the materials. Some of the one question which is really interesting. Clearly, there's an ecological interest here, right, of recycling and so forth. And I think that's absolutely fascinating how you've captured what I don't think people think historically as building materials, bringing them back. So one person asked, do you use what kind of bonding agents? Are there bonding agents, and are they edible and biodegradable and eco-friendly, right, in the same way?
Yes. So when we're 3D printing with the powdered materials, the binding agent that we're jetting on the powder is mostly water with a little bit of alcohol. So sometimes we literally just mix, alcohol and water, like isopropyl alcohol and water. But sometimes we actually print with alcohol, like sake or vodka. So yes, it's edible.
Excellent. All right. So that's another great. In following up on this, you talk about powder-based printing, and you mentioned the recycling using laser sintering. I'm trying to now read your colleagues, which of course they're way over my head. But the laser sintering printing process, or do you add? So you do add a binder, right, to that. So I think that question was answered. But somebody wanted some more just general information on the 3D printing process. The hardware, like where did you get these printers? Are there ones, how did you think this through? What types of modifications have you had to bring to the robots in order to do this sort of work? So you talk a little bit about that.
Yeah, so for the powder printing, we started by using Z-Corp printers, which are no longer made. So all of the printers that we did this research on starting back in 2009 or 10 are out of commission now. So I actually haven't printed anything in powder probably in about 2 years because you can't buy the print heads to jet the material on. So there are other companies that are making 3D Systems and Desktop Metal are making powder-based printers now. So maybe if I can get a big enough grant, I can buy a new printer. And then other printers that we're using for the clay, those are actually pretty affordable. There's a company called Potterbot that makes those clay extrusion printers. And then the robot arm is something that we commissioned someone to make just for us. Yeah.
And do you see these as potential? I mean, obviously there's an artistic kind of approach here, but do you see these as practical applications of building sustainable homes?
Yes, absolutely. I mean, we're just still in the proof of concept phase.
Mm-hmm.
Additive manufacturing has been around, 3D printing has been around since the late 80s. So it's not that old, right?
Right.
So we and there are others around the world who are working, prototypically to start to build housing, and it's coming. I think it's going to happen in the next 10 years. Yeah.
Just how long did it take to print the Casa Covida?
It took about a month, and that's because the mud has to dry, right? So if it were plastic, we probably could have printed it in a week.
Got it.
It was pretty fast. Yeah.
So one last question, and then we'll probably have to go. One of your colleagues asked, "Are you familiar with Mario Cucinella's work on 3D printed ceramic buildings?" And if you are, wanted to comment. If not, I guess now you have homework.
Okay, thank you.
So I guess that's not one you're familiar with yet. So you can reach out to John Loomis and ask him about it, and you all can chat.
Okay.
Well,
I know John. Perfect.
Awesome, great. I just want to thank you again, Virginia. This is what I love about this is it's the interplay of art and architecture and the activism that you bring to the work as well, that there's a real application here to this material work, that you're talking about sustainability, about challenging border politics and so forth. We're just at San Jose State incredibly proud of your work and your efforts, and the fact that you're here with us leading. So thank you so much again for this talk. It was absolutely amazing. For colleagues on this talk today, look out in about a week. It'll be up on ScholarWorks and you can watch it again. And I'm sure Professor Sanfratello will be more than happy to answer questions via email and other mediums about this work. And thank you again, everybody, for tuning in. We really appreciate it.
Okay, thank you.